Okay, all good?
Yep.
Okay, thank you so much. And thanks to everybody in the audience for coming and joining and spending a whole hour of your time thinking not just about shielding in a broad sense, but specifically, how do we compare different shields and figure out which ones are the best for our applications, different ways of characterizing that. As Lucy mentioned, I'm currently president and chief engineer of EMC United, but throughout my career, I've had the opportunity to work on a number of different kind of projects and platforms. And so that includes things where you house everything in metal and you shield every single cable and you never use chassis for current return. So that'd be most of my NASA projects. Then there are times where you house everything in metal, but then you bolt it to a composite chassis and then you try and shield some of the cables, but not others. That would be the work that I did on the Dream Chaser spacecraft. Of course, in automotive, for the low voltage side, you house everything in plastic, use chassis for current return. You try to avoid shielding anything if you can help it. So those kind of experiences inform the presentation I'm going to give today. But honestly, more importantly, is the work that I've been doing as a member of the working group for a new IEEE standard that's being drafted. And I'll talk a little bit more about the details of that. But it's through going through these different industries and seeing how different industries tackle similar problems. It's all the same physics, but they use different standards to address their different needs. I became a diehard standards geek, and that landed me in the position now of vice president of standards for the IEEE EMC Society. So that also sort of will inform the presentation. So getting to shielding, I think we all want to believe that shielding is kind of that knight in shining armor that's going to save us from, any regulatory failure. And it would be wonderful if that were true. But, even for medieval knights, there was, shielding that was better and shielding that was worse. So some ways that you might evaluate a suit of armor could include, puncture force versus slicing force. What materials are it made out of? How heavy is it? Obviously is going to be a key consideration. The flexibility, can the knight, the warrior actually move in that armor? How much does it cost? And I mean, looking at that picture on the right, you can tell the aesthetics did play a part, right? Sometimes you just want functional, and sometimes you want it to be functional and gorgeous. Probably cost played a little bit less of a role for whoever made that. Now, in the realm of the less perhaps beautiful and less historic, when we're looking at the shielding of either our electronics modules or our cable bundles, or coaxial, instead of evaluating, for instance, puncture and slice force, we do need to know how well does it stand up to shock and vibe, especially for the aerospace industry. If it's going to fall apart, if it's perfectly good EMC shielding, but it's going to fall apart when you're actually stacked on the launch vehicle, it's not going to be very useful. But we still care about materials. We still care about weight. To an extent, we do care about flexibility, right? For cables, we care about that bend radius, whether we can route it all the places that we need to. And even for a box enclosure, we need to determine if, for instance, it's going to be a replaceable unit, or if at some point you might swap cards in something. Is it accessible enough for a user or a technician to interface with while still providing the necessary shielding? Cost obviously is a huge consideration. Aesthetics still play a role, honestly. When you're presenting the options to management, there are things that are going to look better to certain folks than others. It's silly, but it's there. But another thing that we add that the medieval knights did not have to worry about was transfer impedance and shielding effectiveness. And those are two of the key things that I'm going to talk about today. I would hate to get through a presentation without bringing up this particular slide at least once. This is what I call the fire triangle of EMC. And even though my fire triangle looks like an oval, it still has three parts. So I call it the fire triangle because a lot of us learned as kids that to have a fire, you need three things. And those things are fuel, and a heat source and oxygen. If you take away any one of those things, you've put out your fire. So if you smother it with a blanket, you're essentially taking away the oxygen and putting it out. If you pour water on it, you're really removing the heat and putting it out. Well, similarly, to have an EMC problem, you need three things. And those things are a noisy source, a sensitive victim, and some coupling path between them. And that can either be sort of through the air radiation, or it can be conducted emissions and susceptibility through shared electrical wiring. When we're talking about shielding, we are really focused on breaking up that radiated coupling path. Just adding shielding is not actually doing anything to make the source less noisy or make the victim less sensitive, although, I mean, depending on sort of how you look at it. But we're really trying to interrupt that radiated coupling path to take all that noise and, keep it away from our sensitive electronics, or keep it away from the regulatory antenna if you're trying to add shielding to pass, for instance, radiated emissions requirements. It's not going to do anything to solve a conducted emissions or immunity problem. So just to keep that in mind, shielding does some things, but it doesn't solve every problem. So as I mentioned, I'm part of the working group for IEEE P2855. So that P number means that it's a project, which means it has not yet been fully voted on and approved and published. So that basically means that it's in the draft stage. The mouthful of a title for this is Recommended Practices for the Electromagnetic Screening, Effectiveness, Characterization of Cable and Connector Assemblies in the Frequency Range of DC to 40 gigahertz. That committee has bitten off a lot. They were first approved to move forward in 2019. We think we're going to get it out by 2026. The standards process does not move quickly. But in the course of this, we've been bringing together a lot of different test methods and different approaches to try and put in one place these different techniques that are good for different purposes, so that people can really compare apples to apples. And that's going to be sort of a theme as I talk through some of these different methods, not just for cables, but also for enclosures and board level shielding. There are also a couple IEEE standards that are relatively new that I'll mention that have similar approaches, but for, again, enclosures or for board level shields. Some other shielding standards that you might run into, I'll be drawing on IEC 62153, and also 299, 2715, 2716. We'll talk about all these in a little more detail. But just so you know, one of the original drafts of IEEE P2855, the one that we're working on now, had 442 references for cable-related standards. Now, those were not all EMC based, right? They were materials, waterproofing, aging, abrasion resistance, bend radius. It was, anything to do with cables. But it's funny when you think of something that seems so simple, just how complex it can get. And that page after page after page of references really reminded me of how complicated just cabling can be, getting electricity from point A to point B. So what are the things we can measure? And we call these measurands. That's the official term for the things we can measure. And these are all the different things that we have listed in P2855. But I'm only going to focus on a few of them today. So DC resistance, shielding effectiveness, and transfer impedance. DC resistance, because it's super simple. We can cover that in no time. Shielding effectiveness and transfer impedance, especially because in the States, you're going to see these more often than almost any other measurands. And the difference between them, I think, is sometimes not as well understood and is very important. The other thing is that, for instance, magnetic attenuation, that's for a longer seminar, and I'll be giving a longer seminar on November 5th if anyone's interested. We'll talk a little bit about magnetic shielding in that case, and that last one on the list, electric and magnetic polarizability, we'll at least touch on that. Screening and shielding attenuation and coupling attenuation are closely related to shielding effectiveness. They're more commonly seen if you're working in Europe. And transfer admittance is closely related to transfer impedance. So again, I felt like focusing on shielding effectiveness and transfer impedance would be perhaps the most useful for the audience. So starting out,